Welcome back to the Barbarian Meets Coding Vlog and TypeScript Types Deep Dive. This is the last part, and we're going to look into more advanced types like map types, conditional types, and infer. With these type annotations, these type operators, and the ones that you've learned previously, you're going to be in a better position to write a more maintainable TypeScript, as you can transform types, take advantage of other types that are already defined in your application when you're defining new types. So let's get started. Bring the slide. Awesome. So today we're going to talk about mapped types, mapped types, which is the last part of advanced types that I wanted to touch with you in the series. There's a person outside. Mapped types. So oftentimes when doing TypeScript, you will find yourself in the need of converting one type into another type, making a transformation of types. And this is where mapped types come in, because they allow you a very nice way to achieve that conversion. For instance, here is a nice use case to use mapped types that will happen quite often. So here we have a class person. It had some properties like the ones that we've seen in the series before: name, string, height, number, weight, age. And now you have one method that you want to use to update some of the fields of this class. So it could be all of the fields, or it could be some of the fields. And we're going to represent this with an interface right now called person options, right? And then we use object.assign, and we assign some of those properties to the instance of this class person. So this is one way in which we could achieve it with the person options interface that represents those params that we need to update. And when we use it, we can use it like this. We say jamie.update, and then we send age 37 because it was my birthday yesterday. So I'm becoming older and I have more wrinkles. So you can see that we don't need to send all the properties. We can only send one, and then we get the age updated in that person. So what happens is that there's different ways in which we can solve this, right? One way to solve this is to recreate this type, person options, from scratch using optional properties. So we more or less reproduce all the properties in person, and we say name, age, height, weight of the same types, and then we say they're optional. And that way we have a way to represent that data structure type to update the fields inside a person. But if you think about it, this is not super maintainable, right? Because we have two definitions. We have the actual person class. It's already a type in itself. It has its properties, and now we need to duplicate more or less the same types, but just making them optional with a new interface. And then what happens is that if at some point in time in the future we update the interface of person, now we have to go ahead and also update the interface of person options that we have just created. So basically this creates more maintenance for us in the future, because we have a new type that we need to maintain, right? So if we go back to this class person, wouldn't it be nice if there was a way for us to transform the person type itself into like a version of person type that has all the properties optional? And this is where map types come in very handy. So we're going to do a transformation of a type into another type, like the partial type. So here we have imagined a new type called partial, that what it does is it uses generics, and it says partial of t of person is the same type as person, but now all the properties are optional. And this is how you write it as a map type. So here we have this is the syntax I use for map types, and we're using both generics. So we're saying partial of type, we're saying partial of t, so it could be applied to any type. And then we're using this special keyword in to traverse all the properties of the type t, and then we're making them optional. But let's break it down to each of the compounding parts of this map type so we can understand better how it works. And I forgot, look, why do I have? Oh, there's a pointer there, and it's gonna stay there. So yeah, so the type partial, so basically we're saying create a new type called partial, and then it's gonna be based on type t. We're using generics here, so it works with any type that we can imagine. And now we say, okay, it's gonna have all the properties of P. It's gonna have all the properties P of T. So it's gonna have all the properties of that object. We're basically traversing all those properties. And then we're applying an operator on them. This question mark basically says that all these properties are now gonna be optional. And then the return type, we're using an index access operator here. We're saying the return type is gonna be the same. So we're extracting the type of property P in type T. And then this is basically the whole explanation for this partial mapped type. So if you think about this new operator in an union type, if you break it down, it's basically, it works like a loop. So it allows you to go through all the properties of an object and then do different things to them. And that's how we are mapping over an object. We're mapping through all these properties of an object. And then it's nice to and then it's nice to pause a little bit and examine this and realize how we're using these map types result as part of, or they're useful because they build on all the operators that we've seen thus far, all those type operators. So we're saying that we're using generics at the top, then we're seeing the map type with an in operator, then we're seeing that index query operator key of that we saw earlier to extract the properties of an object as a union type. Then we're seeing how we're playing that operator to make them optional. And then finally, we have the index access operator again to access a property, to access a type of a property in an object. In a type. To access the type of a property in a type. There's a lot of types and properties. Type system, the type dimension can get complex. Okay. And now let's look at different examples, other useful examples of map types that we can think of. So in here, we're using combining a map type with an intersection operator, and then we get we get to transform a type, and then we get to extend the type with new fields. So here we have a partial type that, in addition to that, also adds a timestamp. So it's like the previously that we have before, but now we're extending it using the intersection operator to add a new field timestamp. There, look at that pink. And here we have another map type that, instead of making properties optional, it makes a nullable. And now you can see how the interesting part, the change, applies to the return type. So we're saying that a nullable type T, a nullable of T, what it is an object that has the same properties as the object we're basing ourselves on. And now the return type, it can be twofold. It can be two different things. Either the type of the property itself in the original object or null. And using this, in this case, transforming the return type, we're getting the ability to make an object nullable. Here we have another example. This is a read-only of T. So this makes every property of an object read-only. And then this is exactly or super similar to partial of T, but now instead of using that question mark operator to make them optional, now we're using read-only to make it read-only. If we want to make the reverse, a writable of T, so we do minus read-only, and that allows us to make all properties not read-only, so all properties writable. Here we have another type. This is even more complex because now we are using two generic types. What this object allows us, what this new type allows us, is to pick some of the properties only of a given type. So create a new type by picking some of the properties of other type. And this is how you would use it. So we have this type ageless person, which is the result of applying this map type pick to the type person and sending a union type with all the properties that we want to get. Then if we read it slowly, we say pick of T, so it's of a type T, and K, which extends key of T. So K is a union type that can be one or more of the properties in type T. And then you can see that instead of traversing like we did before, that we traversed the key of T, so we traverse all the properties of type T, now we're traversing P in K, so K is only a subset of those properties. and then the return type is the same. We use the index access to get the type of the property. So if you think about it, a nice way to think of map types is like in terms of functions. So they're like functions that work on types, very similar to the map function that we have in array prototype, but instead of working on values, it works on types. So it transforms types into other types, and you can see them as transforming a collection of properties with some types into a collection of other properties with other types. Awesome. So all of these map types that you've seen are so useful that they actually can build in TypeScript, and they're called utility types. So read only of t, partial of t, pick t of k. There's a lot of these types that are built-in utility types that come ready to be used in TypeScript. And you can find great examples of how to use these different utility types right in the TypeScript documentation. So you go there, you go to utility types, and you will find all of them here with examples for you to use. Very useful. Now for the end, we have conditional types and infer. And this is going to wrap our view at advanced types in TypeScript. Conditional types and infer. So conditional types let you choose between types based on a condition. And you're going to see how that works in an example, because that's the best way to explain it. And then infer lets you infer generic types, which you can then refer to in conditional types, particularly in the true branch of the conditional type. And again, this is much easier to understand when you see an actual example of a map type using a conditional type. So we're going to jump into that. Okay, so let's imagine that we have some code, and in the code you want to log that something happened, and now we're using a logger to log that information. And then what we're doing, we're saying that, okay, we're logging that my dog ate my mom, and then we put a timestamp date.now. And now we're writing some tests, right? We're writing some tests. We want to assert that that method was called when we exercise some system under test. And in order to do that, we're going to use a mocking framework, and we want to record some expectations on a mock and say we expect that this method will be called log with this information, and that's the scenario we're going to cover right now. So this is how it looks, the implementation for this mocking framework. It has a way to ignore arguments that are called argument matchers. And then what we start doing is we record the expected behavior in our mock. So, and it has the same API, or a very similar API than the real object. So that logger.log, that's we're saying, okay, we're expecting that whenever we exercise the system under test, we're gonna call the logger log method with this argument, my dog ate my mom. And then because timestamps aren't very reliable, we don't want to tinker with the clock, we just say that we're gonna ignore the second argument, it's not that important. And then we test system under test, and then we verify that the logger was called, and that's gonna pass or fail our test. And this is a special method that is in this mock class that is called $verify, that verifies that the expectation was met, that it happened. So now we have a mock that matches the mock type behavior, but it patches all methods to allow for argument matchers. So this sounds a lot like a transformation of types, right? So now when we want to or need to model this in the world of types, let's see how we do it. Let's see how we represent it in the type dimension. So this, we're gonna create a new mapped type, because we're transforming an object, a type, that we want to mock into a mocked version of that type. And that's transformation, therefore mapped types sounds like a good candidate for that. So we create this new type mocked of t that represents a mock of a type t. It should be generic because it should work with any object. And now we're saying, okay, for every property p in type t, we're gonna do the following. We're gonna say that, and now it's when we're gonna use a conditional type. So we say if the type of that property, we're using index access, so the type of property p in type t, if that type of p extends this other type. So basically what we're asking is, is this type a function? Is the type of this property a function? And then we're saying basically if it extends, and that's the type annotation for a function. Ignore the infer for now, or don't ignore it. So we're using with infer u and infer r. Basically, it's like we're saving those types in a variable. So we're saying that basically we're saying, oh, this is a function, and then by the way, save the arguments in the type u and save the return type in type r, and then we can refer to it in the next part. So we're saying, okay, if the type of that property is a function, then return this type. And that is, you're seeing that we're patching both the arguments and the return type. So we're saying, okay, so the type of this property, if it is a function, then we're going to replace the arguments for mock arguments of u, which is going to be another map type. And then the return type is also, we're going to patch it for mock r. So basically we're replacing, we're saying if it is a function, then instead of using the former type, now it's going to have this patch type that basically makes it mockable or useful in tests. And if it is not a function, then we don't need to do anything. So yes, if it is just a property, yes, return the type of that property. So basically it's traversing all the properties, checking if it is a function. If it is a function, then we patch it. If it's not a function, then we just use the normal type. And then in the end, we use the intersection type operator to extend the mocked of t, to extend the original type with a bunch of methods that are only available in mocks, like that $verify, for instance. And then, yeah, you saw how that is where infer comes in. So we're saying you need to use infer there so we can refer back to it here. So we're saying whichever type is there, now we're gonna actually patch it or extend it or transform it. That's the right word, transform it, because we're using map types. So this part here is a conditional type. It's when we say, if this type is a function, then patch the function. If it's not a function, then it's a property, then return the normal type. So this is the conditional type. And then just for completion, so the mock arguments of t, this is also a map type, but this is simple. This is where you're saying, go through all the properties in this type, and then they can either be the original type or it can be an argument matcher. And because they can be either of those, then basically what we're doing is that we're allowing the consumer of this mock to provide either the normal type or these argument matchers, like the ignore argument. Otherwise, we wouldn't be able to do it because the function would expect normal types and not argument matchers. And that's it. That's it for mapped types, conditional types, and infer. I know that this can be very confusing, so don't be too hard on yourself if it sounds weird or it sounds confusing. It's okay for you to go back where I started talking about map types and going through it once more so it slowly sinks in. And the next thing that you should do is to open the TypeScript playground and just play yourself with map types and try to create partial on your own, try to create read-only on your own, try to experiment with different map types and conditional so you understand how it works and can internalize it. Because this is very hard to understand because it's super abstract. We're normally super, we're very habituated, we're very comfortable with values, with just programming, but then when you add the layer of types on top, it can be quite confusing because it's so abstract. Everything is like one step away from the actual program. It's like a different dimension, the type dimension. Awesome, so now we're gonna finish this talk with asconst. This, I know where to put it, so I put it in the end. But it is a nice thing to know that it exists. It's a way to make objects immutable. So it's something that you can apply in the world of types, in TypeScript, to make objects immutable, completely immutable. So here we have an object literal, which is like a dummy object, sed, which has a property text, value hello. If you use asconst, when you declare it in the end, and this only works with object literals, what you do is that you make all properties read-only. So now this, from the TypeScript perspective, this object is completely immutable. You cannot change it. The cool thing about this is that it's deeply immutable. So if you have a nested object with objects inside itself, as const applies to all the objects, and that's inside that object. So this is what we would call a deep immutable. So this is really useful to creating immutable objects. Use it in thy code. Where are my hands? They're here. It's kind of here. It's like I'm a handless person with no hands, but they're here.